Wait a second or two. Sound will kick on then. Should be good to go. So today is Thursday, right? You guys just, you completed the quiz on half-lives, radioactive decay, etc. And then, here's the video lecture for today. Obviously, I'm making the link right now as we speak, so I can't put the link on here yet. And then, the video lecture, should be a little shorter. You guys can take a peek at it at the second half of class, maybe finish it off for homework tonight, and then be ready for as we kind of go into the team meeting tomorrow and Monday. So tomorrow and Monday we'll kind of move into nuclear fission, maybe start into fusion at some point. Okay, and I'll have more detailed plans obviously for this, coming up on sort of this weekend / Monday. And then to be determined the due date for the Chapter 19 book questions. I don't know when that'll be yet. But keep working on those. It's not a big group of them. I think it's a good idea to kind of plug away at those right away. Okay. So today we're primarily talking about this guy, right? You guys, it's this dumb little cartoon sketch, and I think that we all have an idea who this is. It's Albert Einstein, right? The famous scientist. Probably even to this day, he's a person that a scientist that is recognizable to you guys, as 15, 16-year-olds, right? Still to this day. Okay. So obviously, he's a pretty renowned scientist, known to this day. And here's my dumb little sketch, and you guys all know who he is, right? What's he famous for? E = mc squared, right? You probably in grade school you heard that equation. It sounded cool to say, and we're going to get into some significance of what that equation really means. Here's a scientist that, a theoretical physicist, a scientist that was born in Germany, fled Nazi Germany, and worked in the Swiss patent office. He kind of was not a guy that really liked school all that much, but was really gifted in mathematics and physics, and ultimately finds his way into sort of developing these different theories of theoretical physics that ultimately have structured and really changed the way that we think about matter in our universe. He died in 1955, right? And we still know, you guys still have an image in your mind, my dumb cartoon sketch, right? You knew that was Albert Einstein to begin with. And we're talking about his work a little bit today. The other interesting thing about him is that, you think about like the rock stars of today, or the pop stars or popular culture stars of today, famous NBA basketball players or things like that. In his time, in the kind of the 20s, 30s, and 40s, and even up until his death in the 50s. Think of Albert Einstein. He was this is really goofy. I mean, he's this crazy-haired kind of scientist, right? But he's as sort of renowned and famous as many of the famous rock stars of that time or of this time, to give you some comparison. And it's kind of weird, in our society, in our culture, in this modern era. Here is this kind of tiny little dude that worked in theoretical physics, but he was as sought after and looked upon within that same respect within popular culture. Partly because he kind of had this funky look, and partly because he was a little bit of an eclectic personality, but also because he was super duper smart, and he came up with some ideas that were very much tipped the balance of how we understand our universe. So let's get into that. So Einstein's famous equation, right? E = mc squared. Now there's some components of it that probably you guys haven't necessarily always seen or heard of. This little delta symbol, the little triangle. You've probably seen it just as listed as E = mc squared. Well, what does this revolve around? It revolves around the mass and energy relationship. Here's sort of the deal, right? We understand, like, you can burn a log, and it gives off some heat and energy and light and things like that. So we understand there's a relationship between mass has potential energy, right? And Einstein understood that, okay? But he also looked at it upon how does this relate to the energy that's given off in radioactive decay or nuclear reactions. And that's really what this sort of relationship stems from, is it's going to look at the change in mass that happens in a nuclear reaction and relate that ultimately to the energy that is given off. Okay, let me just check something. So, so the equation first, let's just kind of define what we're looking at. So delta E, delta M, and then C squared. So delta M is the change in mass. That's the mass of the products minus the mass of the reactants in a nuclear reaction. The delta E is the change in energy. It's the energy of the products minus the energy of the reactants. Okay, so we're always taking, when we talk about the delta, again, the delta E or delta M, it's going to be products minus reactants. Delta means change in, right? So, and then finally, C is the speed of light. Okay, so to kind of summarize a little bit before we get into this a little bit more formally, what did Einstein really build a relationship between? His realization was that in nuclear reactions, there actually is a tiny amount of mass that is lost. Now, that tiny amount of mass might seem sort of insignificant, but the fact is that these particles and these materials are moving around at incredible rates of speed. And he realizes that this relationship of these particles that are being lost and sort of seemingly disappearing, mathematically, you multiply that value times C squared, and it gives you the amount of energy that's being given off. Now, this amount of energy is ultimately, compare it to any sort of chemical reaction, is a really large amount of energy, right? It's the old analogy I've been using, like, you get in a fender bender, but all of a sudden 3 city blocks blow up. It shouldn't happen. That is sort of an analogy to help you understand that tiny amounts of mass that are lost within these radioactive decay or collisions or bombardment equations results in large amounts of energy. Well, why is that? It's because of the fact that the multiplier here is the speed of light, and in addition, it's squared. Okay, the speed of light is 2.998 times 10 to the 8th, or 3 times 10 to the 8th meters per second, right? Well, that's a big number. Well, not only that, that number is squared, right? So Einstein really put this relationship of energy and the change in energy to the change in matter, or mass, I'm sorry, within nuclear reactions, and made it so this was calculatable, okay, ultimately, okay? So, it says in a spontaneous nuclear reaction, the products have a lower mass than the reactants. So the interesting part here is, like, we've kind of hung our hats on that when we've been balancing these nuclear equations, is that we've said, you balance the mass number, you balance the atomic number below, and then both sides of the reactants and products need to equal. Well, in reality, the kind of the secret that I'm sort of giving up right now is that there actually is a tiny amount of mass that is lost. And again, it's not a lot though, right? It's tiny, right? But it is measurable, okay? So in the case of any sort of nuclear reaction, the products have a lower mass than the reactants. So in other words, the delta M is negative, okay? So therefore, if the delta M is negative, if this value is negative, a negative number times a positive number that's squared is still going to give us a negative number, right? Now, in the world of kind of thermodynamics and study of energy, anytime that we have negative delta E's, a negative value in front of a change in energy, this negative value means that the energy is being evolved to the surroundings. It's being given off, okay? If it was a positive delta E, that would mean that it's going to take that energy in, okay? The reaction is taking the energy in. So negative energies, negative delta E's, equate to energy being given off. A lot of times these are referred to as exothermic reactions. They are given off energy, and then whereas endothermic reactions take energy in, they would have a positive delta E. Okay. So the missing mass, okay, this missing mass that Einstein realized, right? It's almost immeasurably small in chemical reactions. So the reality of it is like, in some ways we sort of wink, wink, In chemical reactions, the conservation of mass, Dalton's law is true, but there's a little bit of mistruth to it. Okay. The delta M is almost immeasurably small. So we just kind of turn a blind eye to it and say we're good with the conservation law of conservation mass, Dalton's law, when we're talking about chemical reactions where we spent 90% of our year this year. Okay. But in nuclear reactions, okay, it is larger, and it's still small. Don't get me wrong, but it's large enough now that we have to kind of make some statements that really the law of conservation of mass doesn't necessarily totally truly apply. And this is sort of the premise behind what Einstein does in creating this relationship between matter and energy, is that he makes and understands this statement that, what's happening is this matter that's sort of seemingly disappearing in these reactions is actually converting into energy. Okay, so matter in these nuclear reactions is converting into energy. And not only that, the amount of energy that's giving off is quite extraordinary. Okay, so still, just to kind of put some perspective on this, the amount lost is small. In nuclear reactions, it's maybe only about a 0.002% change in mass. That's tiny. I mean, 0.002% of anything, that's a tiny amount, right? But it is a measurable amount. It's a tangible amount that we can measure and understand and actually equate this to, right? But as we said a few minutes ago, a lot of energy is actually released. So even though the delta M is a tiny, tiny number, the amount of energy that is actually released as a result of it is quite large. And why is that? Okay, is because that the particles and material that is released and created as a result of this radioactive decay is reaching at or near the speed of light. They have a really incredibly high kinetic energy of movement. And it's squared in this relationship. So Einstein realized that it's not only are these particles that are decaying and falling apart and disintegrating everywhere, are they moving really fast, but in addition, this numerical relationship is that the fact is that this relationship is squared. Right? So multiply that tiny number times a really big number that's squared results in some pretty dang big numbers over here, right? And that's really as kind of deep as we got to kind of get into this in some respect. But now what I want to do is we're going to kind of build Einstein's equation into a usable form. Because here's an issue, right? The classic E equals MC squared. Okay. Well, if we look at this from a perspective of, can I solve, this is a statement of equality. The energy on this side, or the units on this side, I should say, need to equal the units on this side. Well, the units on this side would be grams times meters over seconds squared. And the units on this side would be joules or maybe kilojoules. Well, I can tell you right now, joules or kilojoules does not equal grams per meter squared over second squared. This relationship doesn't compute. You see, Einstein was working under the relationship of not necessarily sort of using the mathematics until later. He was more or less proposing the relationship. And the mathematics gets a little deeper, right? But Einstein hung his hat on wanting to be able to explain his theories to the average person. He didn't want his theory of relativity and this mass and energy relationship to be so far beyond anybody that it couldn't be, 65 years later, 70 years later, it couldn't be explained to a class of a bunch of high school sophomores, high school chemistry teachers. He wanted it to be accessible. That was a really big goal of his. Because of who he was. He wanted the science to be accessible to people. So when he would explain his relationships, he would sort of explain them from a different perspective. And then he'd get into the higher order mathematics on his own to prove to the science community of what this relationship meant. So what are we doing right now? We're going to take Einstein's sort of equation and kind of rearrange this a little bit. Okay. So you got to kind of stay with me. I don't get too caught up if you're like kind of, you know, freaked out about this sort of mathematical gymnastics that I go through. At the end of the day, we're going to reassemble Einstein's equation into a usable form. If you get kind of caught up in the middle here, it's okay. Remember, you guys know me. I don't like just putting an equation up on the screen or up on the board and saying, here it is, guys. Blech. Doesn't make any sense. How do you get there, right? How do we get from E equals mc squared to the equation that we're ultimately going to get to, right here? Well, here we go. This is what happens. So the E equals mc squared, if I take c squared, right? So this is the expression for c squared right here. That's 3 times 10 to the 8th squared, and then it's meters squared over seconds squared. Okay. It's found that 1 joule equals 1 kilogram times meter squared over second squared. 1 meter squared over second squared is equal to 1 joule per kilogram. Blech, that sounds like a lot. We're not going to spend a ton of time on this. So what we can do is that we can ultimately plug in, because this is an expression of equality, we can plug in this relationship here, okay, in place for those units. Okay. So we've kind of rearranged Einstein's equation. Okay, so 9 times 10 to the 16th joules over kilograms times the delta M equals the delta E. Now, here's kind of the deal. Like, you know, we could leave it in this form, but joules, remember a joule is a really tiny unit of energy. Like a joule is how much energy it takes for me to lift an apple above my head. It's like almost nothing. And a kilogram is a pretty large unit of mass, right? A kilogram is 1,000, you know, 1,000 grams. It's a fairly large unit of mass. Well, when we're talking about changes in mass in these nuclear reactions, we're talking about, I mean, infinitesimally small amounts, you know, less than 1 gram, right? When we're talking about energies, we're not talking about 1 joule, we're talking about kilojoules. So this next little sort of rearrangement gets us into changing that expression for c squared into kilojoules per gram, right? So joules over kilograms, 1 kilogram contains 1,000 grams, 1 kilojoule contains 1,000 joules. I run the math here, and ultimately I get 9 times 10 to the 10th kilojoules per gram times the delta M of any nuclear reaction will give me the delta E, the energy that's being given off. Okay. So this here in this big red box here, this is what I will call and tell you is the usable form of Einstein's equation. Okay. Because what does it do? It unifies units. If I have a change in mass here of grams, grams over grams cancels. What do I end up with? Kilojoules. Kilojoules is an expression for energy. Okay. It makes us able to use his equation by clearing up that issue of the units. Okay. Vice versa, let's say I measure the amount of energy that's being given off, and I need to solve for, say, the mass. Okay. Well, if I divide by kilojoules over grams, and I bring kilojoules over here, kilojoules are going to cancel. I'm going to be left with 1 over grams, which is the same as grams, which would be the units for the delta M. So this form of the expression is needed to unify these two parts of the equation. Okay. So this is really key. All right, so let's jump into like an example, and so you guys sort of understand. Before we do that, I want to give you guys sort of a bit of an idea, right? The average decay of a radioactive substance will give up about 1 million kilojoules. Okay, that's a lot, right? We did the kind of calculate the energy in a can of Coke the other day, right? I believe we're doing that in class the other day. This is, in a standard chemical reaction, if you compare that, right, nuclear reactions will have or possess, somewhere between maybe 1,300 or 1,400 times the amount of energy, this average decay. I think we did the Coke, calculate the energy in a can of Coke activity, or maybe we're going to do it coming up. I forget. Okay. Bottom line is, more than anything else, it's not necessarily about the numbers here, is that chemical reactions, while they do give off energy, exothermic chemical reactions give off energy, compare this to nuclear reactions. Like we said, it's like the fender bender that blows up 3 square city blocks. Okay, you know, it's sometimes it's upwards of maybe 13 to 1400 times as much energy in terms of their number of kilojoules than what you'd experience in sort of the normal chemical reaction. Okay, so compare that to, sorry, right here it is, right here. Brain fart, guys, sorry. You know, a glass of Coke, okay, contains, oh no, there we go. A glass of Coke contains like about 180 food calories. That's 180,000 science calories. Remember, food calorie is a kilocalorie. Multiply that by 4.184 joules per calorie. That gives me about 753 kilojoules. Well, so if I take, you know, 1 million divided by 753 kilojoules, you know, that's about 1,400 times as much. That's a lot, right? And we get an idea about foods that we consume. We have, you know, we get caloric energy from that. We've drank a can of soda or Coke or Mountain Dew is going to be somewhat comparable to, and we feel that kind of energy from it, right? Certainly, though, by comparison, nuclear reactions carry a lot more energy with it, okay? And it stems from this relationship of the fact that it is mass that is being lost and converted to energy, but it's moving at incredible rates of speed, okay? So let's jump into a question here, right? So this is a question that I believe is right out of your book, just so you guys know. And I'm going to kind of walk you guys through it. And I do suggest that you guys maybe, as we go through this, maybe you go back and, you know, pause, rewind, go back and look at, if you're, you know, slow down, look through this carefully and slowly. So I've got radium-226 decays into radon-222, and it gives off an alpha particle, which I'm reminding you again is a helium atom, right? You're going to calculate the delta E in kilojoules when 1.02 grams of radium-226 decays. Use the table on page 558. Okay, well, this is in the back of your book. I've taken an image of that table. We're going to use that table ultimately. So maybe you want to get your book handy to be able to look at this and prove to yourself that these numbers came from somewhere. To calculate the delta M as if 1 mole decays. And then you're going to find the delta M when 1.02 grams decay. And then you're going to ultimately find the delta E using Einstein's equation in its usable form. Okay. All right. So I would suggest maybe just kind of pausing for a second, getting all this kind of written down, and getting yourself set up to be able to show kind of the work as we kind of navigate our way through this. Okay. Right, so part 1, right? So the first part was to calculate use the table on page 558 to calculate the delta M if 1 mole decays. So this table is based upon masses as far as 1 mole of these different samples. So we have reactants minus products, right? We said that, or I'm sorry, products minus reactants. I said that backwards. So the delta E, let's just again prove this to you. The delta E is the energy, I'm sorry, the mass of the products minus the mass of the reactants. So we need to look up the mass of the products. Well, what's the product? The product is radon-222, okay, and helium, right? So radon-222 is right here, and alpha particles, which is helium, is right here, right? So that's these two values. I wrote them in here. That's the products. And then we're going to subtract that from the mass of the reactants. The reactant, right, was radium-226. So I look up radium-226. There's its mass. So that's this value that I've plugged in right here. Do the math, right? And I'm going to, you have to trust me a little bit. You guys want to pull your calculator out to prove it to yourself. But if you do the math, that means that the delta M in this particular reaction is negative 0.0053 grams per mole. Remember, this chart is based off of grams that will be lost per mole, right? So that's kind of the tricky part in this question, is that you have to understand is that now we're not, we're not looking at a mole that is undergoing decay. it says that we took not a mole, but 1.02 grams instead. Okay, so that 1.02 grams is going through decay, right? So we got to find a way to convert how much actual mass is decaying. So how do we do that? So the delta M has to go through kind of a conversion. Here's based off of, if I had 1 mole of radium, I would lose the negative 0.0053 grams. Well, I'm going to multiply that by the molar mass of radium-226. Well, radium-226 has a molar mass of 226 grams, right? Because it's a specific isotope. So the grams are going to cancel, moles are going to cancel. I'm going to end up with, okay, ultimately, and then I multiply that by, sorry, my bad, the amount of grams of radium that we had to begin with. So think of this as basically we're making it so we figure out how much mass is being lost based off of this initial amount. Okay. This mass that is being lost here is based off of if we started with a mole of the reactant. Well, we didn't. We started with way less than a mole. Okay. So now my converted value for the delta M ends up being negative 2.4 times 10 to the negative 5th grams. Okay, so there's 2.4 times 10 to the negative 5th grams of substance is lost. That's a tiny number, right? Tiny number, okay? Well, now all I gotta do is I gotta plug that value in. So my delta M gets plugged into this equation. I multiply it by 9 times 10 to the 10th kilojoules per mole. Grams are gonna cancel, and I'm gonna end up with kilojoules for the delta E. Okay, so that's, again, you gotta guys gotta kind of trust me. That's the delta E. It's going to be negative 2.2 times 10 to the 6 kilojoules, right? 10 to the 6, right? So tiny amount of energy that's lost, but because it's going by that multiplying factor, C squared, right? Huge amount of energy being given off. You know, and again, remember, a negative sign means that it's being given off. Negative delta E's means energy is being given off by it. Blowing up, falling off, going out into away from the reaction, right? And then again, 2.2 times 10 to the 6, right? So that'd be 1, 2, 3, 4, 5, right? And one more, right? So that would be 1, 2, 3, 4, 5, 6. Oops, that should be a 2. My bad. Okay, so that's 2.2 million kilojoules. That's a lot, right? It's a really big number, right? So again, just to kind of put some perspective on this, right? Einstein and other scientists of his day and those that were studying radioactivity realized there was certainly a huge energy potential from this. And Einstein's equation really sort of proves that, among other things that we're going to end up talking about. So the decay of isotopes and radioactive substances has obviously a huge energy potential. But it is variable, okay? Each different radioisotope is different, and sometimes, obviously, these types of radioactive decay cannot be controlled very well. But certainly humongous energy potential. To give you some perspective, right? I have a little statement here, okay? Nuclear fusion reactors that create electricity. About 4.5 grams of uranium-235 is the equivalent of 15 tons of coal. So what's 4.5 grams of uranium-235? Uranium-235 is a radioactive isotope that's used in fusion reactions that we're going to learn about next week. 4.5 grams, that's about like 4 or 5 big paper clips in your hands. Nothing, right? Hardly anything, right? That's compared to 15 tons of coal, right? That's basically 15 dump truck loads, okay? 15 dump truck loads is the same as 4.5 paper clips, right? So again, it gives you an idea about the humongous energy potential that radioactivity and nuclear decay really has within it. And that's why, it was obviously and is still an area of significant study, and especially as we reach stages of where different fossil fuel sources are running low and running out. Eventually, these limited resources are going to run out. We have to find ways to be able to create energy for our planet. Now, there's some other things that I want to just sort of say off the cuff before I sign off here, that are interesting sort of tidbits about Einstein's equation. There's some things that come out of this that become kind of weird and exciting and different and neat. And we'll have some more discussion about this later on. But part of the weirdness factor of as this material is moving at high, incredible rates of speed, there's some things that come out of this equation called the theory of relativity that start to blow people's minds. Okay, the primary thing is this: is that in actuality, as things start to move at incredible rates of speed, time actually slows down. Length compresses. When we're talking about materials moving at high rates of speed, we're talking about materials moving at high rates of speed, some interesting and strange things happen. Okay, so we're going to get more into that later on. And this sort of equation, this relationship of energy to matter, had opened up kind of a can of worms that Einstein sort of released upon our world in terms of a new understanding about how matter exists. Okay. All right. That is it, guys. Thank you. We will see you later.